Hi class, welcome to lecture 6 of our data structures and algorithms course. Today we are looking at the ordered array data structure. In the lecture, we will do a recap of a data structure and what arrays are. Then we will introduce ordered arrays as data structures and look at the significance of ordered arrays as well as the algorithms that we use to perform data structure operations. We introduced in the past lectures data structures as mechanisms that enable us to organize and store a large collection of data. Whenever we are defining a data structure, we must indicate the elements, the data elements, as well as the operations that can be performed on those data elements. An array is a foundational or fundamental data structure that enables elements of the same type to be stored in a contiguous block of memory. An array is characterized by a fixed size and its elements can be accessed by using its index or position. So the basic properties are that you have homogeneous elements which are of the same data type, a fixed size which is defined at creation time and cannot change during runtime, contiguous block of memory where elements are stored in adjacent memory locations and therefore can be accessed randomly. Zero-based indexing where the first element is assigned index 0 and the last element is index n-1, where n of course is the number of elements. Direct access where you are able to access an element directly by specifying its index. And then static memory allocation where you are not able to resize the size of the array during runtime. In the last lecture, we looked at an unordered array as a data structure and looked at the 4 operations that we might want to perform on an unordered array. We looked at insert, where the algorithm simply starts at the beginning of your array, looks at the last available operation and inserts the element at that next available index. Search starts from the beginning of your array, comparing your search key to every element in the array until it finds a match or you reach the end of the array and you have not found what you are looking for. We also looked at deletion, where you find the element and where you search for the element, and if it is found, you remove it and you shift subsequent elements so that you do not have holes in your data structure or your data collection. Then we have the display, which enables us to iterate over the array, the data collection, starting from the beginning and outputting every element that we have in the array. So this is demonstrating how the search element, if you are looking for search key 17, it will actually compare it to every index until you reach the end of the array. If you delete, that is what happens. Then let's quickly, for today, we are especially interested in the linear search. We want to see what really happens when we are searching in an unordered array. The first step, of course, is to, if we look at it from an algorithm point of view using pseudocode, our linear search, which is the name of the algorithm, will require an input array as well as the target element that we are searching for. The first step is to initialize the variables, one to keep the length of the array, another to indicate whether we have found what we are looking for, but of course initially it's false, and position is going to indicate in which position was it found in the array, the index. In step 2, we are going to iterate through each of the elements in the array, starting from I equal to 0 to n-1. What we are going to do is to check whether the element that is stored at the current index is equal to the target. If it is equal, then we set found to true, position to the index, and we exit the loop. Otherwise, we keep incrementing n until we reach the end of the array. So at the time if we reach the end of the array, then our found, and we have not found what we were looking for, our found will still be false. This is why in step 5 we are now outputting the result. We say if found, which means that found is equal to true, then we can indicate that the element was found at index, and we indicate the position that was set using the value I. Otherwise, we return that the element was not found in the array. What you need to note is that if you have a large collection, linear search may not be efficient, because the number of comparisons that is required for you to identify or to determine whether the element, the target, is found in the array is unfortunately just too much. Implementing linear search, and in this case I am doing it line by line. So I have defined this method as a static method because in any way we are passing the integer array as an input to the method, and then we need to specify the target. Then we need to initialize the three variables: n to the length of the array, found to false, and position to -1. Then we have the for loop that will enable us to iterate through the elements of the array, and we need to compare if what is found at index I is equal to the target. When it is equal to the target, we set found to true, position to I, and we get out of the loop. Then in step 5, we are returning the results. If found was set to true, we indicate that the element is found at this position. Otherwise, if found is not true, then we need to indicate that the element was not found in the array. So this is a direct implementation of this algorithm in Java. Now we are introducing ordered arrays as data structures. So, and in ordered arrays, we are basically still using the array data structure, but we want to enforce the operations, the insert operations, to ensure that the elements are maintained in a specific order. The order can be ascending or descending, where elements are arranged either from the smallest to the largest or from the largest to the smallest. And of course, we want to, the way that you're going to be ordering or determining how ascending order or descending order should be implemented, it's going to be based on the relationship between the elements. And if it is ordered, it will make it easy for us to perform some of the operations, such as the search operation, efficiently. You therefore need to have a comparison function that makes it easy for you to determine how to order these elements. What we see here are three instances of array. As you can see, the first one is not ordered. The second one is ordered in ascending order, while the third one is ordered in descending order. We want to have ordered arrays because they facilitate efficient searching. You can use the binary search algorithm that we will discuss here to enable quick searching. Also, when your elements are ordered, it makes it easy to find the nearest neighbors of the elements, so it's much easier to perform range queries. Then it also enables us to do insertion and deletion with reasonable efficiency. We will actually look at these points later on. Ordered arrays are used in database systems for indexing and search operations, where they are also used for information retrieval to enable faster information retrieval and sorting tasks, especially when you are dealing with large data sets. And if you also use ordered arrays, this can lead to optimized solutions. So for example, by using binary search algorithm, you can drastically reduce the search time. Let us now look at how we are going to be implementing the data structure itself. So the class that implements the data structure is called ordered array, and we are going to be defining our instance variables as private for information hiding purposes. We still have to keep track of the array, which is an array of longs. We call it A here, as well as the number of elements. In our constructor, we specify the capacity and create the array for longs, and indicate that at the time that we start this new ordered array, we have 0 elements. But because we might want to return the size, we will also, or the number of elements, will also define a method called size that simply returns the number of elements. It's important that we do this because n-elements is actually defined as a private variable. Our display method is not that different from the unordered array. You can see we simply have a for loop that starts at position 0 up to position n elements minus 1, and we are simply printing the contents of A at position j for every element, and then we print a new line after that. Our delete method also not that much different. We specify the value we are looking for, and we are first going to implement a method called find. For now, find can be implemented using various algorithms, maybe the linear search that we talked about, but it's going to return the index of where that element is found. When the index is equal to n elements, we know that it is an invalid index because your indexes are running from 0 to n elements minus 1, and therefore when j is equal to n elements, we know that we didn't find what we are looking for, therefore delete must return false. Otherwise, we have returned a valid index, and we must then start another loop that starts at position j and going up to the end of the array, and whatever is in position k plus 1, we copy it to position k. Once we have copied over all the elements, we are going to reduce the number of elements to by 1 and return true. So which means that we find what we are looking for, and then we shift the elements that are after that to before and decrease the number of elements. Of course, it might also be advisable that you start with the last element. So you start with k equal to n elements, going to k greater than j and k minus minus, and then you are going to be copying the elements in that way. Let us look at method insert. And in method insert, we want to add an element to our array. In this case, we are starting at position 0. Of course, we need firstly we are assuming that these elements are stored in ascending order. So we need to find the correct place to insert the elements. So we start at j equal to 0 up to n elements minus 1. And as if we find a value that is great, if we find a value in the array which is greater than the value that we want to insert, then we must break because this is the position where we need to insert it. So, but for as long as this condition is not true, we are going to increment j until this condition becomes true. Then when we have gotten out of this loop, we have exited this loop, we are going to set k to n elements, which is what I was suggesting previously. Then we have k greater than j. It needs to be greater than the position where we want to insert the long value, then k minus minus. Then what we are going to be doing is copying what is at k to k minus 1, so that because we are starting from the end and we want to create space. And we do that for all the elements that are position greater than j. Then once we have copied all those elements, we will create a space at position j, and that is where we are going to insert the values and increment the number of elements by 1. That is our insert method. So let us now look at how we can implement those methods or test those methods inside an application. And we said in addition to the data structure, because all those methods that we looked at are in the data structure, we also need a main method that is going to test the data structure. In this case, we create a data structure with a maximum size capacity of 100. Then we insert these values 77, 99, 44, 55, 22, 88, 11, 0, 66, and 33. And you can see that in this case, we have inserted them in no order. Then we can search for an item, for example, with key 55 by calling method find of the array. So we say if array.find, the search key is not equal to array.size, because remember, find method is going to return the index, but if the index is the same as the size of the array, then we know that we did not find what we were looking for. But if it is not equal to the array size, we know that the search key is in the array. So this is going to be invoking the search function, or the find function that will then tell us whether the element is found or not. Then we can display the contents of the array. We can even call method delete to remove some items and display again the contents of the array. The method that we have not really demonstrated so far how it works is the search method, which we have also used under find. So here it's called find or search, but let us quickly discuss how this method works. Since our array is now ordered, we don't have to use linear search where we start from the beginning to the end of the array. We can use binary search. And with binary search, we want to minimize the search range so that we make sure that we do not have too many items that we are comparing with. So when we are given a search key, we can compare the search key to the middle value, which is in the middle of the array that we are searching in. If the search key is less than what is in the current index, then we know that it is going to be less anyway than all the items that are to the right. If the search key is greater than what is in the current index, we also know that it is going to be greater than all the items that are to the left of the search range. And therefore, depending on the comparison result between the search key and what is in the middle index, we can determine where to focus next. Should we focus on the right or should we focus on the left? So binary search enables us to define the bounds, our search range. Where do we start? Where do we end? And we keep subdividing until we find the element that we are looking for, or the element that we are looking for is not in the array. If we look at the visual representation of this array, let's say that we have a lower bound. Initially, we have values that are stored from indexes 0 to 24, and these are the values. Our search key in this case is 17. If you compare 17 to the middle element, which is 28, if you compare it to the middle element, then you will find that 17 is actually the middle element is 12 because we have the middle index is 12 because we have 24 indexes, and what we have here is 28. So if you compare 17 to 28, you see that 17 is less than 28. So there is no need to even bother about the indexes to the right of 12 because we know all the values here are going to be greater than. So we can actually reduce our search range so that we focus from index 0 to index 11. Then if we look at the middle element from 0 to 11, it is going to be index 5. Now we compare our search key, which is 17, to the middle element, which is 12. Again, here we find that 17 is greater than 12. So we know all the values here are not going to be greater than or equal to 17. Therefore, we should not bother. We should reduce our search key to index 6 to index 11. Therefore, our lower bound in this case needs to change to 6 while our upper bound remains 11. Then when we look at the middle element, in this case it is 17, and we have found what we are looking for. So with the binary search condition, with the binary search algorithm, the initial condition is that you must have an array that is sorted either in ascending or descending order. You need to be able to identify the midpoint in the array, and you compare the target element to the midpoint. If they match, you have found what you are looking for, and therefore the search is successful. If they do not match, you look at the search range, the relevant search range that contains your element, depending on whether it's smaller than the middle element or greater than the middle element. And you have to keep repeating this process until you find the target element or your search space has now reduced to 0. Looking at the actual algorithm, again in this case, we assume that you pass the array and the target value to binary search. The first step is to initialize your variables, your lower bound, your upper bound, which is going to be the length of the array -1, found to false and position to -1. Then we have while true. What you should do is, which is the actual binary search now, identify or compute the middle element, compare what is in the middle to the target. If it is equal, then set find to true, set the position to middle, and then you get out of the while loop. Otherwise, if it is not equal to the middle, determine whether it is smaller than the target, because if what is in the middle is smaller than the target, then we need to move the middle to after the current point, after the current middle, by adding 1 to mid, and that becomes our lower bound. Otherwise, if it is greater, then it means that we need to remove the higher upper bound so that it is before the middle element. This is why we have high equal to mid minus 1. But at some point you might have high, which is low, which is greater than high, which means that we don't have any more elements in this array, and therefore we break. Then you can output the result to indicate whether you found the element that you are looking for at a specified position, or the element is not in the array. Looking at the implementation line by line, low set to 0, high set to the length minus 1. Yeah, need to be high length minus 1 actually. And then false set, found set to false, position to minus 1, and mid to 0. Then we compute the mid, which is low plus high divided by 2. Then if array at position mid is equal to the target, we set found to true, position to mid, and we get out of the loop, exit, break. Otherwise, if what is in the middle is less than the target, set your lower bound to mid plus 1, else you set your upper bound to mid minus 1. And if your low is greater than high, then get out of the while loop. Then you can see to output the results, we just have if it is found, then you indicate that it was found at a specific position. Otherwise, you indicate that it is not found in the array. So this is the direct implementation of this algorithm in Java. But of course, in our book, it's given differently, and we will look at that example now. But if we implement it as a static array, binary search as a static function, we can also define a static array inside our main method and execute the binary search function, which, by the way, returns a string indicating whether the element is found in the array or not. And in this case, we are calling binary search with the static array and a target of 56. Because there is no 56 here, it executed and it indicated here that element is not found in the array. However, if we execute it with a target of 12, which is found in the array, then it indicates that the element was found and is at index 5. Our book implementation of binary search is as follows. We return an int that corresponds to the index of the current element. And remember, this is what we wanted also for our search function, for our delete function. So we set lower bound to 0, upper bound to array.length, and then we have current index running or starting at 0. Then we compute the current index to be the middle element. Then we say if array at current index is equal to the target, if we find what we are looking for, then we must just return the current index because we are returning an int. Otherwise, if the lower bound is greater than the upper bound, which means that there are no more elements and we have reached the end, we return an invalid index, which is NLMs. Otherwise, we have to compare again and see whether the target is greater than the current element, in which case we have to set the lower bound to current plus 1, and if it is not greater, then we have to set upper bound to current minus 1. So this is the book implementation, which matches parallel to, or is exactly the same as this one. It's just that we have expressed the content differently. It's not a static function in this case, it's just a normal function. So what I want you to take note is that the number of operations, comparisons that are required in binary search has drastically reduced in comparison to if we were doing linear search. So for example, if your search range is initially 10, you have 10 elements, then the number of comparisons that are required are 4. If you have 1,000 elements, with linear search you will have to do 1,000 comparisons. If your element is the last element, here is a maximum of 10 comparisons. If you have 1,000,000 elements in your data collection, maximum 20 comparisons. If you have 1,000,000,000 elements, maximum 30 comparisons. So you can see really that binary search drastically reduces the number of comparisons that are required. So, but of course the question to ask yourself is how many comparisons will be required given a specific range. So for example, if you have 128 elements, we know that you need at least 7 comparisons. If you have 1,000 elements, you need at least 10 comparisons. How do you compute this? It's by using the logarithm function. So 2 raised to what power, because you are always subdividing it into half, 2 raised to what power will give you the range that you require. So you find the inverse of raising 2 to the power by using logarithms, and you'll be able to compute that value of S. Also note that this approach that we have used, where you are continuously subdividing your search array until you are no longer able to subdivide it further, is called divide and conquer. You have a large problem, you subdivide it, and you solve the problem using this approach. So it's called divide and conquer approach. So far, in our data structures, whether it's using ordered arrays or unordered arrays, we looked at the use of primitive variables, but of course this is not representative of real-world data storage structures. In the real world, you have a combination of many fields where you might have a personnel record storing the last name, first name, age, ID number, and so forth. And the library catalog for a book, for example, might contain an author name, document title, edition, etc., etc. So it's very important to keep in mind that when we are creating real applications, our objects might be more complex than the primitive types that we have looked at so far. In the book, we are given an example of a person object that has a last name, a first name, and an age. And we can represent this object as a class using these instance variables, a constructor that initializes the values of the instance variables, and then we have get and set methods that enables us to change the values of the instance variables. We also have a toString method that enables us to, we are overriding this from the class object, of course, where all objects inherit from, and this represents or gives us a string representation of a person object. But for every person object, we have also introduced the display person method that just returns the toString for that specific person. Our data structure then will have an array of persons. Again, we have called it A, and we are keeping track of the number of elements. For our constructor, we indicate the maximum capacity, create an array of persons with that maximum capacity, and initialize our number of elements to 0. To display, it's not that different when we are traversing the data collection. We simply start at position 0 of our array up to n elements minus 1, and for every element that is stored at a specific position, we just call method display person, which calls the toString method for that specific person object. So traversing an array is not difficult, but we now need to look at the other three. Remember, for every data structure, we are interested in those 4 operations: traversing, inserting, deleting, and find. So this is the traverse method. Method find looks as follows. You have to specify the search name for the person that you are looking for. Start at position 0 up to the last element, but now for every person that is stored at index J, get their last name and compare whether that last name is equal to the search name. Luckily, the last name is a string, and we know that equals compares these 2 objects and returns whether they are the same or not. So if we find that they are equal, we get out of the loop because we found what we are looking for. This is why we have break. And then we need to compare whether the reason why we got out of the loop was because j became equal to n elements. At this point, if j is equal to n elements, we didn't find what we were looking for. Therefore, we have to return null. The reason why we are returning null again is because our find method returns a person. But if there is no person, then you have to return null. Otherwise, you have to return a reference to a person that is found in position j. That is our find method. Looking at method insert, here I have given you the code for inserting in an unordered array. So assume that you just insert at position n elements and you add n elements plus plus. But of course, I want you to create a method that enables you to insert in an ordered array so that you still maintain the order according to last name. So this is an exercise for you. Method delete, you can see that again it looks exactly the same as the method delete for when we were inserting in an ordered array of integers or longs. But in this case, what needs to change now is we are looking at the last name. So we still have to say if the person at position j's last name is equal to the search name that we are looking for, you get out of the loop. And if your j element at this point, your j index at this point is equal to the number of elements, you can return false because you didn't find what you were looking for. But if it is not equal to that, then you have to start shifting elements so that you can delete the element or overwrite the element that was at the found position j, and then reduce the number by 1, decrement the size. Then if you go all the way here, it means that you were able to delete and therefore you return true. So what you need to then take note of is that the type of the array in this case was changed to an object, which is person, and the key field that we used in this case was a string, which is last name. So we cannot compare the last name using the double equals operator. We had to use the equals method. So as we have indicated here, a at position j dot get last name dot equals to and the search name. Also, in this case, the insert method creates a new object of type person and inserts it in the array instead of inserting a long value. But of course, I want you to give me the code for inserting the person in such a way that your ordered array still remains ordered. In the application, nothing will change in this case. We specify the maximum size. You insert the items. So for example, in this case, I'm inserting Evans party and 24. It's because our insert method actually had a string surname, string first name, and then the age to correspond to the age of that person. And we insert these 5 records. After inserting the records, we can then print them out. So we call display array contents, call method display, and then we can search. For example, in this case, we are searching for Stimson, and then we have person found, which is going to use the find method that returns a person to assign that person to found. But when your found is equal to 0, is equal to, not 0, when your found is equal to null, you know that you didn't find what you were looking for. So this is why when your found is equal to null, we print can't find the search key. But if your found is not equal to null, we can indicate that we found the person, and because we have stored that record in found, we can even call display person, which is a method defined in class person, to display that record. We also have delete. We are testing delete. So we first delete Smith, delete Yee, and then delete Adams. These are specified as search names, and then if these are found in the database, then it will display the contents without the records that were deleted. So when we execute that application, immediately after insert, it will say displaying array contents, and it shows the contents as shown here. Then we searched for Stimson. Because it's not found in the records, then it says it can't find Stimson. Then we delete. After deleting, The last name that is displayed is Evans and Hashimoto because Smith was deleted, Ye was deleted, and was deleted. So you can see that from the deletion, we looked at what are those names, the last names that are found there. So in summary, we can see that arrays in Java are treated as objects. You create them using the new operator. You need to wrap your array class in the data structure so that you can prevent it from being inadvertently altered. If you don't do this, for example with method insert, you can see a person will just be able to insert directly in an array, but you want that to be defined as a private variable, and then you can define the operation that enables or that specifies where that record is going to be inserted. So this will make it simple for the user class. They would not even have to bother about how exactly the insert operation is implemented. With unordered array, we are able to insert the data in our collection as fast as possible. But if we use the linear search for searching and deletion, it takes a long time. Binary search can be applied to an ordered array, which makes it very fast for us to look for information, but sometimes unfortunately it's a bit slow to insert because you have to create space where you need to insert the item. Linear search requires time that is proportional to the number of items in the array, while binary search requires time that is proportional to the logarithm of the number of items. For now, just take my word for it, but in the last lecture, we are going to look at how much time is required to implement these algorithms. Thank you very much for sticking with me up to the end. This is the end of this session.